So, which quadrant do those limits isolate? Keep in mind the quadrants are 1, 2, 3, 4. Second quadrant, yes. This is going to be a region in the second quadrant because if you look at x's limits, x going from left to right, the first thing x hits is the left end of a semicircle of radius 1. So x will enter on this boundary, okay? X will exit the two-dimensional region at x equals 0. So you stop right there. So just based on the x limits, that's what our region looks like. Only based on the x limits, but you can't use x alone. X's limits guarantee that I enter at the left end of the semicircle and I exit at the y-axis, x equals 0. But then when you cross that with the y limits, when this region is flattened to the y-axis, what does it flatten out to?
0 to 1.
0 for y to 1 for y. So y begins at 0 and ends at 1. So you really only have that quarter of the circle. It should be the second quadrant chunk of a circle of radius 1, which translates to what polar limits? R goes from
0 to 1.
0 to 1. Theta stems
Pi over 2 to pi.
pi over 2 to pi. So this should become 0 to 1 for r, pi over 2 to pi. Your integrand is pretty straightforward. That's already e to the r squared, which by itself, no known antiderivative. Thank goodness, every time you convert to polar, what happens? There's that magic extra r that pops up to multiply with your function and turns what previously couldn't be integrated into something that you can integrate. Now this one, yes sir.
What is that extra one?
That's called, I refer to it as the Jacobian, but if you go back to those polar notes,
Jacobian?
and I think, Chauncey, I think you were looking at them a second ago.
How do you spell that?
Every time you convert to polar, because your underlying rectangles are not dy by dx dimension, they're dr by d theta, they're sort of rectangular sector circles. So this was kind of derived a little bit haphazardly. I kind of rushed through it. But I showed why that extra r is there because it's in the notes for the polar section if you want to double check it. So every time you convert to polar, every single time, if you're going to polar, I mean the limits come from some kind of circular region of the xy plane to get this, but there's always this extra r. Don't forget the extra r that pops up when you make a polar double interval conversion. And then this works well with the u sub. If you integrate r, then what u sub would you do?
R squared.
U equal r squared. Du is going to be 2r dr. Thank goodness we have that extra r in the mix. You see?
Yeah.
So that way you're integrating 1/2 e to the u. And so that becomes 1/2 e to the u. I'll go ahead and not make Nick panic anymore.
1/2, not 2.
Not just Nick, but all those others. So undo your u if you want to, and then plug in your r limits. Your r limits are from 1, so you have a funky answer. You get 1/2 e to the 1 minus 1/2 e to the 0, which is really just 1/2 e minus 1/2.
Okay. So how do we know which limits to put on the inside and the outside in this particular one? Because I have them reversed.
I almost always do dr d theta. If you can do d theta dr if you want to.
I
just
mean,
put-
there's no problem.
Yeah, this pairs with this pairs with this, just like x and y.
Yeah. Sorry.
Always from the inside out. Not the final answer because I haven't integrated theta yet. But what's that going to be multiplied by when I integrate theta?
R squared.
No. I'm done with r. I've done the r integration. All that's left is to go back and do the theta integral. So now theta is my variable. If I integrate this with respect to theta, all this is constant. So what would my antiderivative do?
It's just theta, isn't it?
Constant times theta, yeah. And then you plug in your theta limits. This is one, since you're integrating over constant limits, you could have factored it if you wanted to. So weird looking answer. That constant times pi is my top limit, pi over 2 is my bottom limit. So really that's a pi over 2 times all this half e business. So anything equivalent to that should be your answer to this funky interval. You can factor out the 1/2. You can put it in the numerator. Now just being silly. I mean, just there's other ways you can do to state the answer. But what's the toughest part about this one? Was it the graphing of the region? Translating? I think based on my experience with students, I think it's usually translating this for some people, turning that into a picture. But keep in mind, you know, for a circle of radius anything, you know, if I turn this into semicircles of radius 16, no, that's bad. Let's say radius 4. If the radius was 16, that'd be 256. But let's say the radius is 4, so then that would be a 16. And then all these 1s become 16s, but still the same idea. If you see that root 16 minus x squared to solve for y, that's the top half of a semicircle radius 4. If you see x equals negative root 16 minus y squared, that's the left half of a circle of radius 4, semicircle.
Okay. And then
And those pop up a good bit when you're dealing with polar. And I think they pop up on your test too.
can you set up one more of these first that's not in the homework so that we can use
Well,
it
it's
as
not in the
practice?
homework.
So I can go back to those?
Okay.
Please, thank you.
Let me see. Hang on. Okay, this one, I'll admit, this is gonna be kind of tough. Hang on, I gotta do some math.
So, where we say 4
Wait,
minus...
wait,
Sorry.
Okay, sorry, Matthew. That
No,
was
I'm sorry, I was interrupting
I was in
you.
that thought.
So, where we say square root of 4 minus x squared, does that equate to a circle with radius 4?
I don't know,
or
maybe.
2?
Was this with the dam? Yeah, just go with what you know. Go with what you know. It looks very, very, very similar to that.
Oh, yes.
Yeah.
I'm wondering if it's a circle with radius
I don't
2
know.
or
To keep it to
4.
yourself
Okay,
and let
sorry,
everybody else
sorry,
try it out
sorry.
too. I think I screwed something up. The Y limits are okay. I think I messed up my X limits. Yeah, it should be. But I figured out first.
Just square
Yes,
root.
it should just be the square root of 2. Sorry about that. I'm making a mistake where radius is 4 and radius is not 4. Good catch. So yeah, the x limits were just 0 to the square root of 2. Because the first next back is 0. So when you do the first limits, based on y's limits, what you have here looks good, but then x's limits, when you flatten to the x-axis,
This becomes what's left over is beginning at 0. For some reason, I was thinking closer to yeah, so that's why I think, yeah, I'm not sure. Yeah, that makes sense. Okay.
It does, I promise, convert to some pretty nice polar limits. So close. When you do the y direction first, the first thing y hits, according to your picture, the first thing y hits is y equals e. But the first thing y should hit is y equals x. And the last thing it hits is this circle. So you've got the semicircle right there. Yes, if you close your right, she is.
Okay, thank you. So is it?
So it's that. All right. Yeah, there you go.
Is it not? No. Oh man, I didn't even put. Oh, I didn't
And
do
there's something very
that.
convenient about this being the square root of 2.
So
And Bob, at least
I treat that as another function.
Yeah.
Is that
We have a limit.
is that correct? To treat
Well,
this as
and you
another
got it too, I
function?
think.
I was gonna check, like, my.
Oh, the
Is that-
integrated?
I treat this as two functions, two separate.
Yeah, that's the
functions.
entrance function, that's the exit
Okay.
function. That's what those limits stand for. Oh, so this is.
Aha, and then the square root of 2, square root of 2. So
So
it is 0 times y.
that's what that is. Oh, yeah, okay, I was raising it.
Yeah, that's easy.
No.
Yes, so just every single time you add, it's higher if you bring.
Okay, so is it the first
Just be
8
careful.
and the
This should
second
be
8?
so as you go through this.
Second? That's what I started
Just
with.
because of your
There you
That's
go.
right, that's right.
the x values from y.
Okay.
From 0.
Yeah, remember, when you do the inner limits, this is through the two-dimensional region. Once you've done the two-dimensional region, you can flatten it to the x-axis, and all that's left on the x-axis is 0 to root 2. So when you're doing these limits, these need to be two-dimensional graphs.
Yeah.
You enter, when you're going vertically through this region, whatever it looks like, the first thing you hit is y equals x as you enter. And then you exit at y equals the square root of 4 minus x squared. And so this is one of our 4 semicircle equations on the board to your left over here. This would represent, there's something very geometrically convenient about that line. When I graph the line y equals x, it looks like this. Do the origin slope of 1. So y enters through this, okay? And y will exit through this. This is the top half of a semicircle with radius 2. So if I overlap that, it looks something like this. Okay. And then there's no real connection here because there's actually a proper break there. But the first thing y hits is the line y equals x. The last thing y hits is the semicircle. So therefore, all this doesn't matter. Where the line is above the semicircle, that's not correct with this order of integration. Y enters through the line and exits through the semicircle. So this should be the only part we're considering. All right? But then, when you've done the y direction, if this is flattened to the x-axis, what's the interval left over on the x-axis?
0.
0 to root 2. See, I made the mathematical mistake of thinking the circle's radius was 4, and so that's why I put 2 root 2 there. But if you take this radius and project it down to the x-axis, that intersection point right there is root 2.
Use the universal design.
Yeah. Or just keep in mind, what's the convenient geometry of that line?
It's 45.
It makes a 45-degree angle against the x and the y-axis. Okay? So if you project a radius of 2 by 45 degrees down to the x-axis, it gives you root 2 right there. So, y enters through the line and exits through the semicircle, and then it projects x down from 0 to root 2. Where's our region?
The second 8.
That tiny little slice of pie right there, or slice of pizza, or whatever you're hungry for. because that's the only place where you enter through the line and you exit through the semicircle, and it's also consistent with x's limits 0 to root 2. Okay. Told you it was a tough one.
That's good.
But even the line y equals x kind of works pretty well with polar because it makes that 45-degree angle in the first quadrant. So that way, when you convert this into polar, the r limits from the origin outward, r would always go from 0 to 2 because you're dealing with that portion of a circle of radius 2, and then your theta limits in increasing order. Theta begins at pi over 4 right here and spans to right there where you have pi over 2. Okay, so the problem says to convert this to polar, not to evaluate it. So if you convert the integral all the way to polar, and again, the usual order is dr d theta. So if I'm consistent with that, I'll put my theta limits on the outside, my r limits on the inside, but honestly, it probably doesn't matter. The integrand is going to become 1 plus what? R. Yeah.
Times R.
Times the extra r that you convert to polar. So really, if you distribute that correctly, you're really integrating r plus r squared. Convert it to polar, no problem. And the other one that we did, if you can factor this, technically you can factor this as a function of r times a function of theta. It's lame, but if you want to think of 1 as the function of theta, and you're integrating over constant limits, you can integrate the 0 to 2 for r plus r squared, and then just integrate the pi over 4 to pi over 2 for 1 d theta, and then multiply those two results together. Not every time you can do that with polar, but in most cases with our homework problems and with some of when you convert it to polar, you almost always get constant limits because you're dealing with portions of circles or concentric radii.
Is it okay this practice of like writing just the little integrand squiggle with dr equals without rewriting everything? Is that okay?
That's what I've done in the notes. I'll say,
Yeah.
okay, if I integrate dr and then I go straight to half r squared plus 1/3 r cubed, that's fine.
Okay, cool.
That's okay. We need to start triple integrals. All right. We've already devoted about almost 45 minutes of class time to just review, and that's a shameful amount of class time for old stuff.
No, thank you very much.
You're welcome. Triple integrals. The first of, this is technically the first of the last test of this material. We'll do triple integrals. We're going to spherical coordinates and cylindrical coordinates on Thursday night of this week. And then we'll start some more supplemental material. I need to post some more information for the remaining stuff on vector fields and line integrals and surface integrals and flux and all the cool stuff that you get to do with vector calculus. We're not done with vectors. Vectors, you do some vector calculus in the very last chapter, which ties in with a lot of stuff in physics I've never seen. I've never taken the magnetism and the whole flux calculation part of physics. Some of y'all have, and so it's all just flux to me. So I just, I've never seen it in a physics context, but I know how to do it with integration. So it'll overlap with some of the things you've seen with physics, the last chunk of material after we finish this triple integration. But double integrals were set up so that you have a two-dimensional domain in the xy plane, sometimes over a rectangle, sometimes bounded between a line and a parabola, sometimes bounded between concentric circles, so you can use polar for your double integral domain. Triple integrals go 1 dimension higher. So now you're dealing with a 3-dimensional region in space that defines the domain of your triple integral. And it's still just integrating from the inside out. You'll have, z limits, you'll have y limits, you'll have x limits, and then you integrate with respect to z, then with respect to y, then with respect to x. And just keep in mind, it's partial antiderivatives all the way. So when you're integrating z, you treat x and y as constants. Additive constants or coefficient constants, keep in mind that it's their role with that part of the integration. Same thing with integrating the other variables. The other two are going to be constants when you're doing their partial antiderivatives. So if you're lucky to have constant limits of integration, you can set the integral up any willy-nilly way you want to. I mean, technically, you could do, for your choice of integration, there's 3 choices for the first differential. You could do dx, dy, or dz. Then you got 2 choices for the second differential. Then you got 1 choice that locks the third position. So really, there's 6 orders of integration that you can do with a triple integral. Don't worry, I'm not going to prompt you to set up all 6. Just in honestly, most cases, my mindset is to do the z direction first.
Okay.
Because when you're given a description of the region like this, In some cases, they're given to you like this, but sometimes they're described with modifiers like prepositions. Like, your region goes from the xy plane, and the xy plane is z equals 0, and then is bounded above by the plane z equals this. So you say, well, z goes from 0 to z equals whatever that is. And so sometimes you got to pay careful attention to certain prepositions so that it helps you, put your location in space there correctly. But in this case, it just gives you constant limits for x, for y, and for z. So setting up any order of integration, once you choose the order, I'm integrating the function 8yz. So let's say we just decide to do dz, dy, dx. The integration here is not going to be too bad. It's just power rule for y and for z, and x isn't here, so everything here's a constant when we get to doing the x integration. And then once you committed to this, keep in mind, they're kind of like nested bookends. If you commit to dz being first, z's limits have to pair with that integral. So I'll put the -1 to 4 limits here for z. Y is the middle one, so I'm going to commit to using 2 to 3 right here. Dx is the last variable in the integration, so I'll put x limits of 0 to 1 right here. But again, there's 6 different ways you can do this. You can do dz dx dy, dy dx dz, dy dz dx. I mean, you can figure all the 6 you want to, but in this case, any one is going to be fine because your integration is not too terribly bad. So I'll do the same thing I did with double integrals that Matthew was talking about a second ago. So if I do the integral with respect to z, my antiderivative here with respect to z, keep in mind 8y is a constant, so z becomes half z squared. But keep in mind, you multiply the half with the 8, so you can go ahead and simplify that to 4yz squared.
I wasn't having a problem with that. I was asking if we can do that on the test.
Yeah, you can.
Writing the extras.
Yeah, that's fine. I mean,
Okay,
that's
cool.
that's just my shorthand because I do this from inside out. It's okay. And so then plug in these limits for z. Keep in mind who's the constant and who's the variable you're integrating. So when I plug 4 in for z and then -1 for z, that's going to become 16 minus 1. So 4y is 15. You should be left with 60y by the time you're finished with that. So then we're committing to doing the dy integration next. So if I integrate this with respect to y, well, heck, that already is just a function of y. It's just y squared. Bless you. From beginning at 3, well, plug in your 3 first and plug in your 2. So you get 30 times 5, get 150. And then lastly, you got it. These are triple integrals, so expect a third one. By now, you're doing the dx order of integration, and you're at a constant. So when I integrate this constant with respect to x, it just becomes 150x from 0 to 1, and that makes no effect on my 150. So what this, I bless coughs and sneezes and everything.
Yeah,
bless you all for the terrible allergies that the calculus is giving you. But yeah, that's the overall value of this triple integral. Problem is, I can't draw a picture of this. I can't draw a picture of what this 150 represents. Okay? I can draw a picture of this. This region here in space is just 0 to 1 for x, 2 to 1 for y, and then -1 to 4 for z. So that's just some kind of rectangular brick of space in 3 space. All right? But then, that's the domain of inputs that you're plugging into this thing to get the outputs. And then that output set, that output range is in the 4th dimension. So this, if you want to call it a hypervolume, you're welcome to, because it technically represents, I guess the volume of whatever this thing looks like in 4 dimensions, with this being its domain, and then that function being the output values in its range. But I really couldn't call it a volume. You've got all your y values are positive, but some of your z values go negative. So some of the outputs get negative. So we probably really shouldn't call it a volume. So that way it's, but it's just, the total value of that triple integral for this function over that part of space is a total value of 150. Yes?
If one of our restrictions wasn't a constant, would it be that one first, like it was an x squared in there somewhere?
Yeah, that's going to change now. The first example is the easy one when you have all constants. The second one's where you start using variable expressions. Now, I admit, I think I'm picking up a little bit of a three-dimensional visualization graphing deficit from a good bit of you. All right, just from, well, I guess maybe not experiencing as much with the oids and stuff in the first chapter as I probably would have presented with you. So I'm probably going to be a little more liberal with the graphs and the pictures that you get with your triple integrals. Like beginning with this problem, where you actually have variable limits of integration. And some of the problems in the homework are like this. You're given a three-dimensional region in space, not a brick anymore. This is just sort of a tetrahedron cornered in the first octant, coming out to this plane representing the surface, the slanted surface of the tetrahedron itself. So, and again, we can still pick 6 orders of integration, but for the next 3 problems, this problem here on this page, and the next 2 on the next page, I want us to choose, we're doing 3 of the 6 possible orders of integration that we could do. All right, just based on the geometry of this particular solid, so you can see an idea of how you actually set it up. So when you don't have constant limits, if you have variable limits, but keep in mind, on double integrals, the outermost integral is always going to have what kind of limits? Every single time, that outer integral is always going to have constant limits. So the only contenders who could have variable limits will be anything except for the outer ones. In double integrals and triple integrals, heaven forbid you ever do quadruple integrals or quintuple integrals, that outermost integral is always going to have constant limits every single time. It can't have anything but. So if there's any x's, y's, or z's used as integral limits, it'll have to be on the inner 2 of these triples, not the outer one. So, because as you set up your order of integration, you want to kind of do that whole flattening the dimension as you go. See, as we did our double integrals, we would do the y limits in the 2-dimensional region, and then I'd suggested that you flatten it to the x-axis so you can figure out what constant values are left for your single-dimensional x integration, you see? When you're starting with triple integrals, you'll want to choose, like in this case, we're doing the z order first. Once we do the z order, you come in from the bottom, you exit through the top of the shape, z equals what something on the bottom, z equals something on the top, then flatten it to what dimension? If you've done the z direction first, where should I be flattening it next? To the xy plane. So notice when you have this skewed view of 3 space, you kind of got a little projection of the shadow of this shape down here on the xy plane, what it would actually flatten out to. How could you use this to project that tetrahedron to the xy plane?
Make one of them 0.
No, make all of them 0. If I want this to go to the xy plane, make z 0. Yeah, make the z value go to 0, so it turns into the line, this line right here, x plus 2y equals 2. So even if you're given surfaces that represent the top of your 3D space, if you need to project them to the xy plane, let z go to 0. If for some reason I want to project this to the yz plane, let the x variable go to 0. And then right here in y and z, this is the line 2y plus z equals 2. So it works well with planes or tetrahedrons like that, but let's go in and start the limits. So I'm committing to doing the z limits first, the x limits next, and then the y limits last. So when you're doing triple integration, you got to start with a 3D solid for your first limits. The first order is z. And you want to guarantee the same thing is true for triple integrals that we did for double integrals. If I choose the z order of integration, you have to kind of use your visual acuity here. If I draw a vertical ray that represents the z direction, okay, in the z direction, I'd come in through the bottom here, pierce the xy plane, and then where do I exit? If I go due vertical. Somewhere along that slanted plane surface, okay?
0.
Okay, so somewhere, in that order, and no matter where I draw that purple vertical line, am I always going to enter at the bottom at the base, and I'm always going to exit on this tilted plane? Does everybody see that? It's paramount that you see that.
Yeah.
Because see, this tilted tetrahedron right here goes from the xy plane slanted backward to that point of the z-axis. So if you're going due vertically anywhere, you're always going to enter through the xy plane at the base, and you're going to exit somewhere on that slanted plane for the tetrahedron's surface. So when I do z's limits, z enters at the base down here on the xy plane, z equals 0. Okay? But you have to have the exit defined in terms of z. So notice we got this plane right here that's, sort of implicitly defined in terms of x's, y's, and z's. So if z enters at z equals 0, z has to exit at z equals that solved for z. So you need to think of this plane as that equation, because it defines z's top boundary. So let me draw a little vertical rays again that I had there in purple. No matter where you enter, you're always going to enter at the xy plane, and then you'll be inside the tetrahedron for a little bit, and then you'll exit through the top. So that's why, you know, z enters at z equals 0, and then z exits at the actual planes equation. So, but after you've solved it for z, see, that's where you enter, z equals 0. You exit at z equals 2 minus x minus 2y. Okay. Now, we've done z's direction. Flatten what's left to the xy plane, so that way you can do your x and your y limits. You see, once you've done the z direction, you're now in double integral land. You know, you flatten this to the xy plane, and when this thing is sort of flattened down, you see that little triangle right there. If I do an xy plane representation of that, it has an x-intercept of 2, it has a y-intercept of 1, so that base triangle for our tetrahedron looks something like this in our usual xy plane framework. XY plane framework is what I'm trying to say. But I still need some equations. What's the equation of that line?
2 minus x over 2?
Yeah, well, I mean, you can solve it. I just go to your planes
Oh,
equation.
yeah,
If you take your planes equation and let z equal 0, then you're projecting that plane down to the xy plane. So, well, this tilted plane down to our xy plane domain. So x plus 2y equals 2 is guaranteed to be that line's equation, because it's that snippet, it's that trace of the plane in the xy plane where you let z equal 0. So now I'm committing to doing the x direction next. So if I go in the x direction, from left to right, I'm always going to have consistent entrance and exit. So that's good. That's a good deal. I enter at x equals what?
0.
You enter at the y-axis, x equals 0. Now you exit at this line equation, but keep in mind, it has to be solved for x. So it's currently given as x plus 2y equals 2. You'll need to say that I exit at x
2
equals
minus 2y.
2 minus 2y. There you go. And then what's left for our y limits?
0.
0 to 1, because we've sort of flattened it one dimension as we go along. You go from 3D down to 2D, projecting this down to the xy plane. Then you go from 2D to 1D, flatten to the y-axis, and 0 to 1 is all that's left for your y limits of integration. Pretty straightforward.
So
So-
at each level.
At each integration level, you go one dimension less,
Nice.
so you can help isolate those integral limits a little bit better. So if I set this up as a triple integral, those would be the limits I'd want to use. And technically, you don't have to actually use the 3 integral signs. If you go ahead and call that your z, x, and y limits, that's sufficient. Because we know, just to show you, if you did put that on a triple integral, we committed to doing the dz, dx, dy order. Remember, inside is z, so that's where you want to commit the 0 to 2 minus x minus 2y. The middle order is x, so that's where you want to commit your 0 to 2 minus 2y. And then the final order is y, that'll be your 0 to 1.